But that's not the topic that I'm here to talk about. I'm here to talk about near-Earth objects, and I want to start by defining to you what a near-Earth object is. It's basically, I mean, there's a technical definition there on the screen, but basically it's an object that can come close to Earth. And the reason why we care about near-Earth objects is that they can hit the Earth. And there's plenty of evidence that they've hit the Earth in the past. Most of what I'm going to be talking about today is work that is funded by NASA through they have a near-Earth object observation program, which is part of the new Planetary Defense Coordination Office at NASA. So this is work that is, a lot of it is funded by the federal government, and also a lot of the work worldwide is dominated by work in the United States, and it's actually dominated fairly heavily by work that we do here in Hawaii. There's plenty of evidence on Earth that the Earth is being hit. So this is a crater in Canada. So there's a satellite view of this crater, and the original diameter of that crater was about 100 kilometers, and the remaining crater now is about 72 kilometers, or about 50 miles in diameter. The object that hit the Earth was about 3 miles or 5 kilometers in diameter.
Wow.
So before I go any further, we know of nothing that is going to hit the Earth. So you can go home and sleep tonight. So I'm not trying to scare you. I'm just trying to tell you what we're doing to try to protect people and try to find out when something is going to hit. It's not an if something is going to hit. Eventually, certainly over like thousands of years time scale, we are going to get hit. Too big, I mean, basically every million years we get hit by two fairly big, like 1 kilometer diameter objects. And the idea of all of this is find them and push them aside if they're going to hit. You did not have to worry about being eaten by dinosaurs coming here today. And that's because an asteroid, a big asteroid, hit the Earth and basically wiped them out. So in Mexico, you see that where the circle is at the top, that's where the crater used to be from that impact. The object that hit was 10 kilometers in diameter, 6 miles. The amount of energy was 100 teratons of TNT. So this was a very bad day for Earth. It kicked up a lot of dust. It made the planet very cold. Animals that were not warm-blooded didn't survive very well. Big reptiles did not survive. Mammals did. So this was 65 million years ago, led to the mass extinction of dinosaurs. So that's a long time ago. This is the most recent really big impact to the Earth. 50,000 years ago, if you ever get a chance, you're in Flagstaff, if you go to see the Grand Canyon, go see this as well. This is awesome. This is a big crater in Arizona. You see right in the center of this, there was actually a mine. So the person who bought this land was convinced that this was an iron meteorite that had hit the Earth, was going to dig down you see the mine in the middle, and they dug down and they couldn't find any iron. But the iron that hit the Earth vaporized on impact. So it was basically scattered everywhere around this site. This is huge. You have to drive up a big hill to sort of see into it. So if you're in the area of Flagstaff, go see it. It's awesome. More recently, 100 or so years ago, on June 30, 1908, a big object hit in Russia. You're going to see a repeating theme in here that Russia gets hit pretty often, partly just because it's a huge country. This was about 10 to 15 megatons of TNT, so that's a big-sized nuclear weapon equivalent, and we expect something like this once per century. So we're maybe a little overdue for something fairly big. The historical pictures show it kind of just flattened trees everywhere around. There was recently a group of Canadians suggested that this impact that hit in Russia was part of something called the Data Torrid meteor stream. And they were trying to look for objects that might be like this using the Canada-France-Hawaii telescope in July. But unfortunately, the access to the telescopes were shut down. So I think we'll try again to see whether there are other objects. So basically, it's exploring the possibility that this object that hit in 1908 is part of a group of objects that has a similar orbit. So we're looking for other things like that. So there's a possibility that there's an extra risk around July or June, July of objects that are associated with this. So that was an ongoing research to try to explore whether that's really happening. And then, more recently, February 2013, you may have seen some of this. Just about everyone in Russia has a dash cam because there's a lot of insurance fraud. So this was recorded by a lot of people, and I'll show you some of what happened. So this was an object that was about 20 meters or 60 feet in diameter, about a half a megaton of TNT energy released. The energy was released really high in the atmosphere, so nobody was killed by this, but a lot of people were injured by this. And we expect something like this once every 10 to 20 years. So I'm going to show you a little bit of what happened. And the takeaway from this is if you see something like this in the sky, don't go near a window and expect a shock wave after what you see in the sky. Because there's a time delay between, it takes time for this shock wave to make it from the upper atmosphere to where you are. So here's some dash cam video.
Guys,
and this became brighter than the sun.
Get ready. Watch out, buddy. Watch out, buddy. It's gonna get really loud, okay? It's gonna explode.
Big explosion.
It might explode, okay? Watch out.
Oh!
So basically what's happening is it disintegrated high in the atmosphere, exploded into many, many, many pieces. And lots of those pieces rain down onto the ground. Imagine seeing this coming at you when you're driving down the road.
Wow.
So I said there was a shock wave, so I'm going to kind of just show you the shock wave in a little bit more detail. And it's basically powerful enough to knock you off your feet, to basically make you fall over. It's not powerful, this one's not powerful enough to kill you. You just kind of have a look at this. So basically when people saw this thing going across the sky, and they went outside to look at it, and hadn't realized that there was a shock wave on its way. So now you can hear this noise continuing. So there's explosions that also happen further away. So there's sort of sound and shock waves coming from the other explosions as well. But it's quite dramatic. The dogs didn't like it. The car alarms certainly didn't like it. And then we'll look at some more sort of the shock wave.
И сгорел там, да? Ну.
А что думаешь, может спутник? Там уже же падал, они смотрят.
So everyone that got injured basically got injured by the broken glass or by getting knocked down to the ground by the shock wave. So knocked off his desk near the window. Very, very scary. What's the garage door? Okay. So basically, we're trying to find these things before they hit. And this object that hit in Russia came from the daylight direction. So we're pretty blind to seeing things coming sort of right in the glare of the sun. We have to do most of our work at night. And we're trying to find these, and the bottom line is about 2 objects of 1 kilometer size will hit the Earth every 1 million years. And a 1 kilometer object is basically disastrous. It's not going to kill everybody on the Earth, but if it hit a populated region, it would be sort of regional disaster. An object bigger than a kilometer would be sort of basically really harmful for the entire planet. This is a map of, so the federal government has a network of detectors that look for, basically, that listen for explosions, basically trying to enforce people, the countries are not testing nuclear weapons. So a nuclear explosion basically sounds just like one of these asteroids hitting the Earth. So this is it took a long time to get this declassified, but this is a map of basically hits on the Earth in a period of 10 or 20 years. And the size of the circle in here is basically showing you how big the hit was. The color, if it's yellow, it happened in the daytime. If it's blue, it happened in the nighttime. You see the Earth gets hit equally in the day and the nighttime. They're much more dramatic if they happen at night because we see them more easily. So I have a few slides from the NASA Planetary Defense Office. So their mission is basically to detect these asteroids, to appraise the risk, and to develop strategies for mitigating or deflecting if the Earth is going to be hit. So where we come in with PanSTARRS is here. So we're part of the search mission. The IRTF on Mauna Kea is part of the characterized mission. So if we find something that is going to hit the Earth, we want to know what it's made of, how big it is, and so on. And there's a radar in Puerto Rico, which is also used to measure these. And then there's a spaceship is going to be sent to a dual asteroid to hit the little one in order to evaluate what happens if you hit them to try to push them out of the way. So that's what we're seeing here. And there's an office in Jet Propulsion Laboratory in Pasadena where they study the orbits of these. So although I said we know of nothing that is going to hit the Earth, that office actually keeps track of 900 objects that we can't rule out as possibly hitting the Earth. The likelihood of any of those 900 objects hitting the Earth is tiny, but we're watching them all. So these are the NASA search facilities. So the Catalina Sky Survey is sort of a competition to us in Hawaii. The PanSTARRS is on Haleakala, and Atlas is on Haleakala and on Mauna Loa. Not on Mauna Kea, but on Mauna Loa on this island. And this is a big military telescope. There's a little bit of work gets done by that. That's been taken to pieces, and they're moving that to Australia. So we get, it's sort of a side product of what it does is the asteroid detections are recorded. And there's a satellite called NEOWISE, which is kind of a repurposed satellite that's also used to measure the size of these asteroids. So there are a lot of this is sort of being done by the United States, but also within a sort of United Nations framework. And there's an international asteroid warning network. So if we determine something is going to hit, that's the group that works on it. If there's going to be an attempt to deflect it, there's another group of experts that will kind of work on that aspect of it. So this is where we are in terms of what we've discovered so far. So about 20,000 near-Earth asteroids have been discovered to date. And you can sort of see the discovery rate over time. So the sort of big surveys like Pan-STARRS are making a big impact in terms of discovering objects, but we've got a long way to go until we completely risk-free. So in terms of what each telescope is contributing, the purple color here is Pan-STARRS on Haleakala, and you can kind of see right now, at least in 2019, we've discovered more than half of the worldwide discoveries of near-Earth asteroids. This is the sobering part of this. So the solid colored pieces of this is what has been found. So this is all objects 140 meters in diameter or larger. So 140 meters is plenty big enough to kill a city or sort of regional disaster. And we have yet to find 57% of the objects that are 140 to 300 meters in diameter. We haven't even found all of the objects that are bigger than a kilometer. In fact, one object that Pan-STARRS discovered just got announced today that's 1.5 kilometers in diameter, 1 mile in diameter. Not going to hit the Earth, not going to come anywhere near the Earth. But that was just a discovery just announced today. So we're still finding even big objects. And I think I have an example that I'll show you a little bit later today to try to show you that this is not easy. And try to explain why some of this is not as straightforward as you might think to find all these things. 30 years at the present rate to basically find most of them. So if something is going to hit, we need to do something about it. And the most viable techniques are called a gravity tractor, which is basically you park a heavy spacecraft at the side of the near-Earth asteroid and use the gravitational force between them to pull it aside. That's only going to work on a smaller object. It's not going to work on a giant object because you can't put a big enough spacecraft there to pull it aside. Another way to do this is a kinetic impactor. So you basically hit it with something big and hope that you hit it hard enough to push it aside. And if that's not going to work, then the other alternative is a nuclear explosive device. And if that's going to be used, that's not done sort of Bruce Willis style where you land on it and drill a hole in and blow it to pieces, eventually explode to the side of it to push it aside. And you hope that it doesn't break into pieces. Could we, I pressed the wrong button, I think. Go ahead. Sorry. So, in a few years, there's an attempt to test this kinetic impactor thing. So they're going to hit this. There's an asteroid called Didymos. It has a little satellite called Didymos B, and they're going to hit the little one with a spacecraft. The reason why they're doing this in a dual asteroid with one orbiting the other is that when they hit it, they'll be able to look at what happens to the orbit of the little satellite, what happens to the period and so on. Because they can't hit it very hard, so it's really difficult to detect how effective this impact is. So in a dual system like this, it's a little bit easier to study how effective this hit was. Here's a little cartoon of the gravity tractor. So there's a heavy spacecraft parked to the side of this, and here's the gravity pulling it to the side. And here's the nuclear explosion method. So this is the explosion happens offset from the side of it, and the expectation is that the radiation from that explosion ablates the side of the asteroid that is facing the explosion and pushes it that way. And a lot of the force is not just what the radiation hits it with, but it's when the material on the surface of the asteroid is basically vaporized, it's going to push out this way. So it makes this extra magnifying force that pushes it. In this case, it would be pushed to the left. And there's the little cartoon of that explosion happening. And there's the direction that the asteroid is pushed. If you want to know more about this, there's a White House document, and there's sort of FEMA plans, and there's even FEMA exercises happen if in case an asteroid, basically to prepare if an asteroid is detected that is going to hit the Earth. So, I'll talk a little bit about what we're doing here in Hawaii. So, Pan-STARRS on Haleakala is doing searches, but then we use the Canada, France, Hawaii telescope here on the Big Island to follow up objects that we discover with Pan-STARRS. And it's not enough to find one of these, you have to get its orbit, you have to be really careful to get this orbit in order to predict whether it's a threat to the Earth in the future. We also have two telescopes called Atlas. One of them is on Haleakala. These are smaller telescopes. So Pan-STARRS is a big telescope that looks at a small area of the sky at a time. Atlas is a smaller telescope that looks at a bigger area of the sky. So Atlas can see brighter objects. Pan-STARRS can see fainter objects. We use the NASA Infrared Telescope Facility on Mauna Kea to characterize objects, and about 20% of the observing time, or 1/5 of everything that's now done on that telescope is related to near-Earth objects in understanding them, characterizing them, and so on. And we also use Hypersu Prime Cam on the Subaru telescope. Subaru is sort of unique in the world that it can look really, really close to the sun right after sunset or right before sunrise. So we're looking for things that are coming at us from, basically from really, really close to the sun with Subaru. And Subaru does that better than any telescope in the world, looking really low down at the sky. So we have to wait for it to get dark, and then we look really, really low down in the horizon with Subaru. So how do we find asteroids? So here's a sort of a simulation. We look for something that's moving. And if you see in between the left frame, the middle frame, and the right frame, there's an object. This laser is no longer working, but you see this object down in the left corner that's moving. Everything else is staying still. So in the middle of this picture is a galaxy, but the asteroid is the moving object in the So there is the asteroid. So most of the asteroids that we see are just ordinary asteroids in the asteroid belt. So we report thousands or tens of thousands of those every night. What we're really looking for is objects with an unusual motion, because the unusual motion is a signature of it being close to the Earth. So this is I guess one of the most bothersome things that I'm going to show you. And I hope that you can kind of understand some of this. The bad guy in all of this is actually Jupiter. So if Jupiter didn't exist, then all these near-Earth objects, the things that come close to the Earth, would go away. They'd either hit the sun, or they'd hit the Earth, or hit the moon, or do something, and they'd no longer be bothering us. But unfortunately, there's a reservoir of new ones. So these are all basically coming to us from the asteroid belt. So the sun's radiation will, over time, push a regular asteroid that might live here. So this is the distance of the asteroid from the sun. So this is 2.5 times the distance from that the Earth is from the sun. So the asteroid is about 2.5 times further than the Earth is from the sun. And when that asteroid gets here, it's going around the sun 3 times for every 1 time that Jupiter is going around. So every 3rd time it goes around the sun, Jupiter's in the same place, and it pulls on it. And over time, that pull again, disturbs the orbit and pushes it into the Earth. And it basically messes with the orbit. So the big bad guy in all of this, the thing that's sending all of these things to us, is Jupiter. So even though these things might hit the Earth, they might hit the Sun, they might get ejected, there's a reservoir of new ones. So this is never ever going to go away even on millions or billions of years timescale. This is a long-standing problem for the Earth. The Earth is going to continue to be hit by this thing. So Pan-STARRS consists of two 1.8 meter diameter telescopes. They have the largest digital cameras in the world, and they image the sky about 2 times per month depending on the weather. So Atlas, in contrast, images the sky, the whole sky, every 2 nights. So Atlas sees the sky more often, but can't see faint things. We image the sky less often and see fainter things. Here's the focal plane of Pan-STARRS. That shows you the size of it. It has 60 CCDs in it, 7 square degree field of view. There's the moon inside that field of view. And it's 1.4 gigapixels. So there's a huge amount of data that comes out of this every night. There's the camera, the detector inside a camera. It's 3 terabytes of data a night. Take an image about every 45 seconds. There's the camera on the back of the telescope, and there's the Pan-STARRS telescope on Haleakala. You can see Mauna Kea in the background. This is sort of a little cartoon of how much of the sky we can see in a month, in a good month, with one telescope. You can see that we can't get to the southern sky. This is why you need telescopes in the northern hemisphere and in the southern hemisphere. We avoid the Milky Way, which is this line here, because there's just too many background stars. This really, really makes life difficult if you're trying to search for asteroids. And this is the part of the sky here and over here where the sun is. So it's very difficult to get close to the sun in here. So this is the whole sky, basically, in sort of a weird projection. So Pan-STARRS also finds a lot of comets. So about half of all new comets are discovered by Pan-STARRS, and there's a decent chance that the next really, really good comet, so we're really overdue for a great, what we call a great comet, a really bright, remarkable comet. And the last 2 of the great comets have been southern hemisphere only objects. So I'll predict, although I might be wrong, the next great comet will be called Pan-STARRS. So we're a big team of people. There's a lot of people working on this project. We don't name them after ourselves, we name them after the telescope. So Atlas names their telescope after their scientists and their workers. But Pan-STARRS sort of takes this team approach that we name it after the telescope. So Pan-STARRS 2 is the telescope that's on the right next to Pan-STARRS 1. And with the second telescope, it basically came into operation this year. We're going to basically double this discovery of near-Earth objects. And there's the Pan-STARRS 2 telescope on Haleakala. And there's the Pan-STARRS 2 camera. And there's the Pan-STARRS 1 telescope. The Atlas telescopes, there's one on Mauna Loa, one on Mauna Kea, and they can scan the basically half of the available sky every night. And there are plans now to deploy another one of these in Chile and another in South Africa. So the intent is to cover the whole sky every 2 nights in both hemispheres. Here's the Atlas telescope on Mauna Loa. There's the detector for the Atlas telescope. So this is one single camera, it's one single chip. And if someone would give me enough money, we would replace all the detectors in Pan-STARRS with this kind of device. It's expensive, but over time, and Pan-STARRS is now 10 years old, this is a new detector. So the problem is that for Atlas only needs one of these. Pan-STARRS would need 18 of these because our focal plane is so large. So the cost goes up from, it's 18 times as expensive basically to build a camera for Pan-STARRS as for Atlas. Here's the Atlas telescope, and I have a little video here of the sky And this is the sky from Haleakala. You can see the sky is not as dark as it is on Mauna Kea. So if you look over here, that glow in the sky over here is the glow of Honolulu. And this glow that's coming sort of lower down is Kahului. So Maui doesn't have nearly as strong a lighting ordinance as we have on this island. The sky isn't quite as dark. So Haleakala is arguably the second best observing site in the world, but Mauna Kea is the best. Well, second best observing site in the United States, if you look carefully. Haleakala may well, I will try to avoid being politically incorrect, it may well be as good as the Canary Islands. The problem with Haleakala is that it has a huge crater, and if there are strong trade winds, then the air sort of comes through the crater in a turbulent way. So if you have strong winds on Haleakala, we don't get as sharp images as we get on Mauna Kea. So here's a little video of the Atlas telescope at work. So the Atlas telescope, now they've turned off all the lights in there. So clearly having lights on inside the telescope is not a good idea, but that's been corrected. You can kind of see how it does its work, and it's robotic. So it's given a task and it just goes and does it. It shuts itself down if the weather is bad, and it kind of does its work. So you can sort of see it over the course of a night. You see the sky going past and Atlas executing its survey during the night. So I want to spend a little bit of time talking about 3 objects now, and 2 of them discovered by Pan-STARRS. One of them arguably should have been discovered by Pan-STARRS, but it wasn't. And after that, I think we're going to switch to the planetarium sort of view of some of these objects and talk about them. So this was a success for a while. It was one of the best objects, if you want to think of it that way, that Pan-STARRS have discovered. It kind of got this name Halloween asteroid. NASA attempted to call it the giant pumpkin and failed. I don't know why they tried to call it that, but this name for it stuck. So on October 10, we discovered a really kind of big asteroid. And this had a diameter of about 600 meters. It came about the same distance as the moon away from us, if it was going to hit. And we would be a lot more comfortable if we had found all of the objects of the size, and clearly we haven't. So 21 days warning, it wasn't going to hit, but it came pretty close. And 600 meters is going to make a